Leverage measure, but before that, I thought I would do some examples on derivatives, particularly the Dini derivatives, which I simply defined and went on. Yes.
You said something on approximation.
I will come to that also. Yeah, that we'll do as we do along measure theory. We'll do the approximation, various approximations will be needed. The reason for that, I want to. So I'll do this example. I must say that historically there are more or less sort of the notion of function itself has gone through a tremendous evolution. Initially the idea of function was more geometrical, like the points on a curve, the ordinate varied with the abscissa and more geometric ideas were of importance. And then came the group which said that the function is something which you express as an algebraic expression, like fx equal to sin x, fx equal to x squared plus 1, and so on and so forth. The first stage was geometric. The second stage was more like algebraic, like it can be expressed as a function, that is, as an algebraic expression in x, the variable x. Well, of course, later they realized that in both these, to start with, there was a tacit assumption that we are talking about the so-called continuous functions, because of the fact that they said that they could draw it. It was a curve. So there was this feeling that it was being drawn. And the expression was one decent algebraic expression, so it was nice and continuous. So there was also a tacit assumption of differentiability. Because you see, you could draw the curve, also sort of the tangent existed, everything was more or less internally assumed that function means this. Then of course slowly a bit of discontinuity was allowed, and Euler and others could construct functions which are expressible as two different expressions. That is, in one region, one interval, it is one algebraic expression, in another interval, it is another algebraic expression. There was a matching problem, and so they had this allowed this bit of discontinuity, and but more or less in the other places there was this differentiability was almost implied. In the wherever there was this algebraic expression, the differentiability was implied. So still a certain amount of differentiability in finite number of places. Then the differentiability except at these points. So it was more or less going along these lines, and until Vittal came along, it constructed this so-called devil function, which said fx equal to 0 at rationals and 1 at irrationals. And there was no algebraic expression, there was nothing like continuity, there was nothing like differentiability. So the entire concept from geometry to algebra went into a sort of correspondence. Point-to-point correspondence was with each point some value is attached, some rule of association. So from algebraic we moved to the notion of the current day version of, not even, I wouldn't say this is the current day version, at least more or less the current day version, the correspondence notion of a function. And I'd like to read two quotes. Just noted down, I was trying to remember it when I was talking to again over a cup of coffee with Harikish yesterday. There is this, when these sort of functions were introduced, first this and then this, there was a very famous mathematician named Hermit who wrote that, I turn away with fright and horror from the lamentable evil of functions which do not have derivatives. And in fact, there was a more sarcastic statement by Poincaré, who is an outstanding mathematician, and a more geometer. Therefore, he was very annoyed with these facts of the derivatives being not existing, such functions being constructed and all. He wrote in a sarcastic manner, in former times, one invented a new function for a practical purpose. Today one invents this purposefully to show up defects in the reasoning of our forefathers. So there is this problem like when all your arguments were wrong, you are very careless sort of thing. But what purpose is served by these functions is sort of, he's lament, he sort of isn't very unhappy with such functions. But life being what it is, this is the correct way of looking at functions. And this is a function whose derivatives we look at anyway, as we go along. We derive derivatives of such functions. Okay. So in fact, when we go to the next stage, when we develop Lebesgue measure and integration and this notion of measurable functions, etc., we will find that even this notion of correspondence has changed. We would rather look at a function as an equivalence class of functions, of such functions, rather than one function. So you could play around with the values at a few points. The correspondence could be changed in a set of measure 0 without affecting very seriously anything that you are doing. So there is a whole lot of evolution that has taken place over the last, particularly over the last 350 years, over the very idea of function itself. So from geometric to algebraic to correspondence to an equivalence class. This is the state we all at present. Once you do the Lebesgue measure integration, this part will be the very general notion of what sort of ideas we have when we talk about a function. Okay, so now with this, we will consider these evil functions which do not have derivatives. So some examples of this Gini derivative. So first, I will make one simple remark, which I call it an example 1. It's the following, or it's a comment rather than, if f of x, so incidentally, up to this stage, almost everybody was, whenever they had, in fact there was another interesting thing that was there for a long time, even in textbooks it was written in the good old days. That is the following. Most of the time, when they talked of such functions, they meant functions which is defined for all values of the real numbers. They never thought of functions defined on a smaller set like an interval or anything like that. For them, function was always defined over R. In fact, there was a very wrong, it was a misconception among people in those days that if I have two functions, if coincided in one interval, they must coincide everywhere. Because for them function meant functions defined over all of R, and if two functions behave like this in the same manner in one interval, they will be behaving everywhere else, which was even written in textbooks, more or less. The reason for that was they had some kind of infinitely differentiable analyticity, somehow there was a built-in thinking process that was there in their mind. But all that was finally spoiled, the party was spoiled by functions. Even at Cauchy time, he started looking at functions on an interval and so on and so forth. And so this notion, for example, if you take any function defined on an interval, you can extend it by periodically, and then expand it in a Fourier series. The Fourier series will convert with under reasonable assumptions will converge to that function only in that interval. In the remaining portion, it may not coincide at all. It will be something else. Okay, so we could do all kinds of funny things. And Fourier, incidentally, Fourier was another person, perhaps was the man who did so many loose things, which was probably the catalysis for modern analysis. All the analysis started because Fourier left a lot of loose ends on that. He said that, he simply said all functions can be expanded as long as they're periodic in 0L, can be expanded in sines and cosines. What is it? What does it mean? The convergence, which function, what is he talking about functions, etc., etc. And that's when Bayer came to try to find out what do we mean by all functions, even then does it work, etc. So real analysis maybe was triggered off in the beginning of the 19th century by Fourier's remarks, Fourier's thesis, which will complete 200 years next year. First, Fourier submitted his proposal in 1807 to the French Academy, and his book was published in 1822. So this is, next year is the, what do you call it, bicentennial? It's 200 years, so simpler way of saying it. Anyway, so I think in a sense, and it took more or less 150 years for people to settle the various questions that arose out of Fourier series, and that triggered off many other ways of looking at functions, expansion, etc., etc. In that sense, Fourier is one of the most important cornerstones of modern analysis. And I was also telling yesterday that, is Hari there? Close your ears, don't repeat it. I was telling him that when I was in college, we had a Shakespeare called Hamlet, and the extremely good critic of Hamlet written by Bradley. And everyone has to quote Bradley in his essays in order to look very impressive and get marks. And even when you are giving a lecture anywhere, scholarly lecture, Bradley has to be quoted. And rather sarcastically, I wrote in one of my essays that if Shakespeare were born today, he will fail in an exam in Hamlet if he doesn't read Bradley. So, in the same way, I think Fourier, if he is born today and takes an exam in Fourier analysis, will flunk. Because he wouldn't understand what's going on. So, that's the sort of generalizations and abstractions that have taken place. Okay. So now let's start with examples of the digit derivatives. Suppose f of x is differentiable at a point then all the digit derivatives will be finite, but incidentally, what are the digit derivatives? Let's recollect the digit derivatives. We look at the point x0, and then we first look at this interval x0 minus delta to x0, the left neighborhood, and then we look at the difference quotients fx minus fx0 by x minus x0, the rate of change, and then we look at the supremum of this as x belongs to this interval, x0 minus delta to x0. Now, as x0 approaches as x approaches x0, that is, as delta goes to 0, this supremum goes as decreasing. Okay. Now, first of all, the supremum could be plus infinity also. Because we have no assumption that the function will be bounded or anything like that, but supremum could be infinite. And as the delta goes on decreasing, this decreasing 0, this keeps on coming down. So the least upper bound exists. So we have this infimum of delta mu dot c. You can look at it this way. Okay. So the correct way of writing it is infimum for overall delta cost. And this is what is known as lim sup of x tending to x naught minus of this ratio. And this could be plus infinity, you should keep in mind. And this is what is known as the Dirac derivative from the left upper at the point x naught. And similarly, you look at the, instead of supremum, you take the infimum, and that could be minus infinity also. So, and then look at the limit as x tending to x naught minus x minus x naught divided by x minus x naught. That will be d minus x naught. Similarly, we have the two right side derivatives. Next, you look at x naught to x naught plus delta, and then define d plus f x naught to be the lim sup of x tending to x naught of plus of fx minus fx naught by x minus x naught, and d plus fx naught to be the limit of x tending to x naught plus of fx minus x naught. So these are the four derivatives at that point. What I want to say, this could be plus infinity, this could be plus infinity, this could be minus infinity, this could be minus infinity. These possibilities are there. In fact, we will give an example where all the extreme cases take place. We will give an example where this is plus infinity, this is plus infinity, this is minus infinity, and this is minus infinity. The worst case situation. We will see a very simple example. Okay, so if you have, so let me start the examples from here. More a remark, if f is differentiable at x naught, then all the linear derivatives will be finite and will be equal and will be equal to the derivative of that part. Then all d plus d minus d plus d minus fx naught, all these at fx naught will be finite and equal to fx. That is the first comment I made. So that's one example. Take a differentiable function and then say I know the linear derivative, all the four linear derivatives. And be the derivative at that point. Because suppose f is right differentiable at x naught, that is differentiable from the right. What does this mean? This means that is limit x tending to x naught plus of fx minus fx naught by x minus x naught exists. We take the difference quotient from the right side, the derivative exists. X naught, x approaches x naught from the right side of x naught. If this exists, then clearly the lim sup and the lim min from the right must be equal, and that must be equal to the derivative, and therefore then d plus fx naught is equal to d plus fx naught is equal to the right derivative. Similar comment for left derivative. Similarly, for left derivative. These are only just two observations rather than.
Sir, isn't if f is differentiable or f is differentiable if
Both are same. F is differentiable at x naught if and only if this happens, this happens, this. Because If these two limits are all these limits are equal, automatically the derivative exists and vice versa. X naught. Right. So now we will take a very simple example. For last 40 years, this has been a very famous question in interviews. Not even linear derivatives. I have kept a notebook in which I have written all the strange answers that have been given. I have never asked this question. Somebody will ask, somebody will answer, and I'll just note down what the answer is. Okay. The fx equal to mod x. Questions will be draw the graph of this function, is this function continuous, is this function differentiable, what are the derivatives, and you will be amazed at the number of answers I have in my notebooks. In fact, that I use for putting multiple choice questions as alternates. That works. In fact, I like long answers because it gives me one option for the multiple choice question. That means somebody's mind thinks that way. Okay. Right, look at this. Clearly, for x not equal to 0, fx is differentiable and f prime x is equal to 1 if x greater than 0, minus 1 if x is less than 0. And therefore, at all points which are not 0, by this remark, all the d plus etc. are there. Therefore, by 1, d plus fx, d plus fx, d minus fx, d minus fx are all equal to 1 if x greater than 0, minus 1. So the only point is at x equal to 0. This is 0, and we will think of the graph. What is that graph? I almost don't know what. With so many answers. This is like that, a 45-degree line. Now look at 0, x naught, and x naught plus delta. Okay, so what about the right derivative? Let's look at whether the right derivative exists. What should we look at? Fx minus f0 divided by x minus 0 and x on the right side of 0, which is equal to fx is x on the right side, when x is positive mod x is x, f0 is 0 divided by x which is 1, certainly it tends to 1. So therefore right derivative exists equal to plus 1. But the moment right derivative exists, d plus exists. Therefore, d plus f0 is equal to d plus f0. Similarly, left derivative exists at x equal to 0. The only difference will be this will become minus x. There will be minus x by x, which will be minus 1 and is equal to minus 1, and therefore d minus f0 is equal to d minus f0. Okay, so that's the next simple example. The next example, let's look at we have seen this function before. We saw that this was continuous at 0 but not differentiable at 0. So it's certainly not differentiable at 0. So again, at x not equal to 0, f is differentiable. And so all linear derivatives are finite and equal. Okay? So that's no problem. The only problem point is x is equal to c. So once again look at 0 and then look at zero x naught plus delta. Okay, so so therefore look at, so let's find d plus and d minus. D plus let us find the right side at any derivatives. So for that you have to look at an interval around 0 on the right side and then look at the interval 0 delta. Now we want to find the difference quotient. What is fx minus f0 by x minus 0? It is x sine 1 over x minus f of 0, which is 0, divided by x, which is sine 1 over x. Now we want to find the supremum of sine 1 over x in this, because we want to find the positive derivative. Now what is the supremum of fx minus f0 by x minus 0, where x belongs to 0 delta?
1.
It's 1 because it oscillates up and down infinitely often near 0. So however small delta it will go up to 1 once and minus 1 once. So the supremum is plus 1 and this will tend to 1 as delta tends to 0. Similarly the infimum is minus 1, it will tend to minus 1. So d plus is plus 1, d plus is plus 1. So for this constant, d plus f0 is equal to 1, d plus equal to 0. Now what happens to the negative derivatives? Same story repeats. Again the difference quotient is sine 1 over x. Again as you go in this, it oscillates infinitely often between plus 1 and minus 1. So this is again d minus f0 and this is again. Okay. Therefore, it neither has the right derivative because d plus is not equal to d plus. Neither has the left derivative, d minus is not equal to d minus. So there is the terrible function. In the sense of Hermite and Poincare, these were those even functions started appearing. We do not have a derivative at all in any sense of the matter whatsoever. Now we will come to the real evil function. Then go to more and more. Yes. For the example, we will come to the Dirichlet function. Zero if x rational and 1 if x is irrational. Now, again, we have to find the, obviously this function does not have derivative anywhere because it is not continuous anywhere. Because if it is not continuous, it cannot be differentiable. So there is no question of the derivative anywhere. Okay? So discontinuous everywhere. And hence has no derivative anywhere. So the only chance is the linear derivative. So let's find the well, it is Discontinuous from the left, discontinuous from the right at every point. Therefore, it cannot have right derivative and left derivative also. So, no chance of any type of left derivative, right derivative, no question about these things at all. So, the only hope, only chance is any derivatives. Okay. Now, let's look at any point x, and it turns out, well, the story could be different for different points. Let's look at, first of all, we should always look at this fx minus fx naught by x minus x. That's the starting point, the difference quotient. But in order to write this, we should know whether x is rational or irrational. And similarly, whether x naught is rational or irrational. So let's split the case into two parts. X naught is rational. So let's look at the dd derivatives at the rational points. Then what is this difference quotient? Let's call it as delta f. So delta f will become now fx minus fx naught is 0 divided by x minus x naught. For convenience, I'll write x naught equal to q, a rational number. Because the suffix I have to go on with q is there. So x minus q. Now if I want to look at I have to look at the supremum, infimum, whether on the right side, left side, all these things I have to look at. For that I should know what fx is. Then only I can estimate. But then for to know what fx is, I should know whether x is rational or x is irrational. So let's look at the 2 points. So now let us look at the right Dini derivative. So we are now looking at the right Dini derivatives at a rational point. For that, I'll take q naught, the q and q plus delta. I take the right neighborhood of the point q. So let delta positive and look at q plus delta. Right. Now, I want to calculate this and then see what is the largest value it can take, the supremum and etc. To calculate that, first of all, if x is rational and belongs to this interval, suppose x is a rational. I want to look at the values of this quotient in this interval. Take a point x in that interval. I want to calculate that quotient. I will calculate the quotient at all the rational points. I will calculate the quotient at all the irrational points. At all the rational points, delta f is 0. Because f0 is, fx is 0, whenever x is rational, f is 0. If x is an irrational point, then that will become 1 over x minus. 1 over x minus q. Now, I want to calculate the sup at the end. Okay. Now, this is always positive. X is here, q is here. So, first of all, notice that this is positive. So, now if we calculate the difference quotient, I will get only 0 rational points and these values are the irrational points. If I want the supremum, it is going to obviously come from here because these are all positive values. Therefore, supremum x belonging to q plus delta of this difference quotient is the same as, you have to worry only about this. Because in those places it is 0. Now what is the supremum? Infinity. It is plus infinity because x can get as close to q as possible. So the denominator can get as small as possible. So the ratio can become as large as possible. So this is plus infinity. And therefore, lim sup is what? Is equal to For every delta that is plus infinity, so the limit is going to be plus infinity. So the right hand derivative, the right degree derivative at any rational point is going to be plus infinity. Now what about the left, the right lower derivative?
0.
The infimum is 0 because these are all positive, the infimum is going to be positive. So infimum delta f x belonging to q plus delta is 0, and therefore d plus fq equal to limit x tending to q plus delta. So we have got the right linear derivatives at rational points, right lower and right upper. What about the left? So now we have minus delta at 0. I'm sorry, not 0, q minus delta. And we have to take a point x here. Now what is delta? It is still 0 if at rational x, and it is going to be whatever that I calculate, 1 by x minus q. Now what about this? That is negative, because x is smaller than q. That's negative, so the soup is going to be that. So therefore, soup delta f is x belonging to q minus delta q is going to be 0, and therefore d minus fq, which is the lim soup of x tending to q minus, is going to be 0. So d minus is 0. What is it? No, okay. Then what is in? It is the same as I have to calculate infimum from this. It is delta f is the infimum of x belonging to q minus delta q of 1 by x minus. What is this? No, minus, because q can go, it can go to as close to q, but it is from the left side, so it stays, keeps the negative sign and becomes larger in value, so it becomes minus infinity. Therefore, d minus fq is equal to limit x tending to q minus. So we got all the linear derivatives at rational points. Analogously, you can calculate the linear derivatives at the irrational points. So exercise find d plus fr, d plus fr, d minus fr, when r is irrational. So arguments will be similar. Now I'll distort this example a little bit more. Fx is x when x is rational, and fx is minus x when x is. So in other words, it switches the parity in the irrationals and retains the parity in the rationals. Okay, so this is a very important function when it comes to proteins. Oh, the previous function is a very important function from analysis. It is the beginning of the notion of characteristic functions. It is the characteristic function of the irrationals. It filters out, in other words, it just selects the irrational numbers and rejects the rational numbers. So it's sort of get one means select, 0 switch off. Whenever the rational comes, it switches off and allows only the irrational numbers. So it's a very important function as we go along, as functions are of great importance in integration. Now here is, this is a slightly different version than the previous example. Previous example was only 0 and 1, but now we have a slightly different. It turns out, okay, let's first of all even write. First of all, what is delta in this case? Take any point x naught. It will be fx minus fx naught. I will calculate one or two of this, and the rest of this I will leave as an exercise and give all the details in the notes. Now look at this difference question. Now in order to supply anything, I must know whether x naught is rational or irrational and whether x is rational or irrational. So again we split the case, two cases, x naught equal to q, a rational number. Now I will do the rational numbers. Again the irrational case will be analogous as the Vittal case. Even the rationals I will do only a few of those things. Okay. If x naught is q, what is delta fx? Fx naught will be now q, because fx equal to x, so q will be q divided by x minus q. Now in order to calculate sup or the imp of this, I should know what fx is, and therefore I should know what x is, whether it is rational or irrational. So this is equal to x minus q by x minus q, which is equal to 1 if x is rational, and it is minus x minus q divided by x minus q, which I will write as minus x plus q minus how many q's? 2 q's by x minus q, or minus 1 minus 2 q by x minus q if x is irrational. Okay. Right. Now let's look at various possibilities arise.
X is not 0.
First of all, if q is 0, then we simply get 1 and minus 1. That's the easiest case. Okay. Suppose q is equal to, so this is the case. Then it's even easier. Delta f is now equal to 0, 1 if x belongs to q and minus 1 if x belongs to irrational. Is that correct? Yes. Minus 1 if x belongs to the irrational. What does that say?
So
The lim sup will always be 1 and the lim in will always be minus 1, whether it's from the right or the left. So what gives the lim sup? Therefore d plus f will be 1. It also be the lim sup is the upper derivatives and the lim in for the lower derivatives. So that's very easy, because whether you are coming from the right or left, if you are rational you get 1, if you are irrational you are going to get minus 1. So 1 is going to be topmost whether you are coming from the right or left, minus 1 is going to be the bottommost when you are coming from the left or the right. So the easy case is what? The derivative derivatives at the point 0. Suppose q is not equal to 0.
Q positive.
There is a problem here. This will take different signs depending on q is positive or negative. So we have to split the case. Q greater than 0, Q less than 0. Okay. That's why it's good to do problems. Get every aspect of it coming into the picture. So if Q is greater than 0, what can we say about this? Now we are looking at the right derivatives. Okay, right derivatives. So I am having q plus delta. I am taking an x in this. Now x minus q is positive. Q is positive, so this is going to be negative and this is going to be 1. So which is going to be the supremum? Obviously supremum is going to be 1. Therefore the sup delta f is 1. Therefore lim sup delta f is equal to 1. Therefore d plus fq is equal to 1. What about inf?
Minus
Inf is now minus
infinity.
infinity. So inf delta f is equal to minus infinity. Therefore lim inf delta f is going to be minus infinity. Therefore d plus f at q is equal to minus infinity. Okay, this is the case when q is positive. When q is negative, this fellow is positive and is as largely positive as you want because of the denominator. So the supremum is going to be from here. And what is going to be the supremum? Plus infinity. Okay. So the sup delta f is plus infinity. Therefore lim sup is equal to plus infinity. Therefore d plus fq is equal to plus. Now what is going to be the infimum? 1. So lim inf is 1. So infimum is 1. Lim inf is 1. Therefore d plus fq is equal to 1. Okay. So if q, or now we know all the right derivatives. Whether q is positive, q is negative, q is 0. What about the left derivatives? Analogous arguments. Now it's a trivial situation. Similarly, find d plus d minus q. Also d plus fr, d minus fr, d plus d minus fr for r. Same arguments. Similar arguments, not same arguments. Similar arguments. You have to identify which is going to give you the sup, which is going to give you the inf. This one last example, there are many go on constructing similar examples. But idea is not clear what you do, okay? Just look at the difference quotient and carefully analyze the sup and the inf. What is the maximum inf? You have start of the number. Fx equal to 1 over x is not equal to 0. Okay. Well, again, what is delta f in this case? Take any point x naught. Fx minus fx naught divided by x minus x naught. Now the problem is whether x naught is 0 or not. Okay. Do we have to worry about other points? No point. At other point the derivative exists. Minus 1 by x squared. So derivative exists. X naught. So we have to worry only about x is equal to 0. It will be this. And that is equal to fx is 1 by x minus 0 by x minus 0, which is 1 by x squared. Okay. Now, what happens to it? What is the supremum?
Supremum
Plus infinity. Lim sup is going to be plus infinity. The infimum is what?
It is also plus.
First of all, infimum over 0 delta is 1 over delta squared, but this tends to plus infinity again. So d plus is equal to d plus is equal to plus infinity. And what happens on the other side? The same. So again, all are everything is infinite. So you could even make a further mess by making it as you could change the sign also, make some of them plus infinity and the other ones minus infinity. You can cook up examples by varying this definition. So there are, this is like a devil function. The derivative simply doesn't exist in any sense of the word. All are infinite. One of the simple devil function. Okay. But idea is now clear. So there is a lot of mess that takes place, but no matter what, if you allow plus infinity and minus infinity, the Dini derivatives always make sense. Always they will exist. The Dini derivatives will always exist. Whether the original function has derivatives differentiable, right differentiable, left differentiable or not, the Dini derivatives, all of them four will exist and provided allow the extended real values plus infinity and minus infinity also. So it's always better to look at Dini derivatives and then decide whether the function is differentiable or not. Okay, so those are some of the examples. One should look at more and more examples as we go on. Right. So now we are.
So in handling discontinuous functions, we had introduced distributional derivatives, and again in derivatives.
See, okay, I'm sorry, I forgot one thing. Namely, I said that first the notion of geometric functions, then the notion of algebraic, then we had the notion of correspondence, then we had the notion of equivalence classes of function as function, then there was this new notion called distribution. The advantage with this notion of distributions was the fact that it had to be interpreted as a function in this sense, but not from point to point, but function to point. So with each, it was a correspondence from a collection of functions called test functions to the real numbers or the complex numbers. You want complex distribution, the real distribution. So this is a slightly different version from this. Up till then, we were all thinking of only functions from the real numbers, Then we said, well, the domain set could be itself. More abstract notions of correspondence. The domain set could be some arbitrary set, the codomain set could be another arbitrary set, and there could be a correspondence. That is also a function for. Now, if you take the domain set as a collection of reasonable functions, and the codomain set as the scalars, then this association leads you to the notion of functionals on the space of these functions, and that with decent properties of superposition and continuity being maintained is what is known as the distributions. The advantage with distributions is the devil nature disappears. They are all differentiable. If we define differentiability properly, then every distribution is differentiable any number of times, and it is again a distribution.
So there are also sometimes they talk about fractional derivatives. Is that the same?
Yeah, that is weak derivative. We are going further and further. Yeah. This is weak derivative. This is all names later. You see, what is weak, what is strong? Derivative. You are estimating the difference quotient in some sense.
But this doesn't mean, I do not mean the concept of equivalence for this.
That's what I said. This is from here. This is a generalization of this notion of correspondence in a more abstraction. The domain is taken to be not a set of real numbers, but a set of functions. But the codomain is still scalars. It's real or complex numbers. So there is all kinds of mixed up notions of functions start coming up. Okay, each one has its own advantages and each one has its own disadvantages. and Poincaré was once wrong. These were not purposeless. Every one of them was invented for a purpose. Okay, that's where I think Poincaré was wrong. He said some of these things were purposefully invented to show somebody was wrong. No, some of them, most of these were invented purposefully to show that something was wrong, but it can be corrected. That's what I think. That part he missed. Okay, but because he took a while to see that this corrects something else. Yeah, in that sense, the distributions get rid of the devil nature. The derivatives are all like this. But they are devils in a sense that I can't draw them. Because the x-axis is a very peculiar collection of functions and the y-axis has to be the number. So how do I draw this? So that devil nature still exists. But it gets rid of the differentiability mess. Okay? It can be differentiated any number of times. Every distribution, its derivative is also a distribution, etc. etc. Okay? To get to that, you must really again do different integration properly, understand the connection between integration and differentiation, and then get to distributions. Okay? But now there are even more complex notions like category and all these things. They are all abstract notions of further abstract notions of the functions itself. So as we go along, we become more and more sophisticated. More and more sophisticated, more and more things we can get, but more and more difficult it becomes. Right. But what is important is all the time you have one foot on the old classical things that you started with, and then you just keep moving, taking these along with you. And that perhaps is again and again, I keep saying, is the difference in the development of mathematics and other subjects. And the main thing in mathematics is, once quadratic equations are established, they are there forever. Then come the cubic, then come the quartic, many things may come. Quadratic cannot be removed. They are there. They have their firm place because it's logically, clearly set up situation. Unlike in physics or any place, you propound a theory today, tomorrow find experimental evidence against it, so you drop that theory like a hot potato and have your new theories. Like I always said that when I was in school, in the early 50s, Second World War was over, atom bomb had been dropped, and Hiroshima and Nagasaki had been destroyed, and our school textbook still had Dalton's theory of atom. Atom is indivisible. First statement. We used to mark it up and write it in the exam. Though already it has been divided and split, etc., etc., etc. So then, after some time, Dalton simply disappeared from the books. But Galois cannot disappear from the book even after 200 years. Brahmagupta's continued fractions cannot disappear from the books even after 1000 years because they are forever true. That's it. Euclidean geometry will remain, but on top of it I will add non-Euclidean geometry. It doesn't mean Euclidean geometry is false. So that is the difference. So that is why it becomes more and more difficult as we go along. The future generation of students of mathematics will find it more and more difficult because they have to accumulate more years of mathematics that has gone on than any other subject. Okay. Perhaps you can today straight away get into field theory. But in order to get into any reasonable algebra, you have to get taught from Galois. And then only, minimum you should start with Galois. Then only you can get in. Even Galois is so difficult to understand. Galois. So it is it's a completely, I think who made that statement, I don't remember. Whether it is, I don't know, somebody said that it is only in mathematics, each generation builds one floor on top of the previous generation's building. Whereas in other subjects, each generation tears off the previous generation and builds another thing again at that level only. They never go up. That's all. Sarcastic anymore. That is one thing which you should sympathize with mathematicians, the students of mathematics. But it takes a while for them to get the groundwork done. You have to catch up with several centuries of mathematics. It cannot be wiped out. So, for example, if you want to really understand what happens in distribution theory, what happens in category theory, or what happens in PDE, you must start why did all happen, who did it, what were the problems, how was it solved, where are we now, what are the questions that are still unanswered. So you have to start from the old, all these things. Okay. Then only you will have a firmer groundwork to answer the right questions. And you will have at the back of mind what went on, what were the examples, etc. etc. Okay. So in that sense, I am now going to look at I put integration. Now, integration also went through a lot of changes as we went along through the changes of the notion of functions. First, there was this differentiation, and then there was this notion of antiderivative. For some reason, the notion integral was used for the antiderivative. Then there is this notion of definite integrals, calculating the area. And you see that again the connection between geometry and this. They always try to calculate the area under a curve. Okay, that's how when the early days of function theory was. It's always connected with some geometrical figure and calculating some geometrical quantity and geometrical objects. So basically, therefore, I call this as area under a curve. This is the whatever that means. We'll just vaguely write that. Now here again, then I say curve, automatically assumes continuous. See, this is the first problem. The early days, we thought that we had a continuous curve. Then subsequently, it was Riemann who sorted it out and allowed discontinuous functions also. And he, up to Cauchy, it was only continuous curves. Cauchy sorted it out up to the notion of continuity and the integral of continuous curves and things like that. But then it was Riemann who brought in this, that you can do these things for discontinuous velocity. So it is the Riemann thing that we will look at. So what Riemann observed, or even Cauchy, first thing that we have to, so we should perhaps write Cauchy first, then for some reason, for an obvious reason, not some reason, it's a differential theory, differential calculus that developed faster first than integral calculus. It was because of the fact that Newton invented, or let's say more from the point of physics, they were calculating the rates, changes, etc. etc. So more of the notion of differentiation and variation along a curve, these were that were along the path that were of importance, and therefore it's the derivative that developed first, and integral came later. But however, it is easier, integration is easier than differentiation in the sense that it demands less from the function than differentiation. Even discontinuous functions can be integrated out. Whereas for differentiation, you need more than continuity. So what is the first starting point for area? I repeat this. The first thing is you take some unit of measurement and then look at a square with 1 unit. Okay, so 1 unit, 1, and you call this as 1 square. This area occupied by such a square is called 1 square unit. Okay, having done that, you next take rectangles which are m units and n units, where m and n are integers. In that case, we divide it into m parts and divide this into n parts, and you find that there are exactly mn squares, so mn square units. First you find the area. But thus far no further. Then what happens if you have 1 by P one by Q, or even just let's say M. To not now full unit, what do? You put P of this, what do you get?
1.
P. So PM 1. So P, the P times this area is just M. So the area becomes M by P. Now again, if this were 1 by Q, you could have put Q of this on this and you will get area as 1 by PQ. Now combine this and this, you can now say that if this is a rational number, this is a rational number, the area will become M by N. So therefore, the area of rectangle with rational sides is equal to the product of the sides. But now, if they are not rational, suppose I have a rectangle which is R and this is S, R, S, for example, not rational, or at least even one of them is not. They are irrational. What do? Then I can approximate this R by a rational number Rn, approximate this S by a rational number Sm, and then take this area Rn Sm as the, so this is not Sm, but this is Sm, as an approximation to this, where Rn converges to R, Sm converges to S. Then this will converge to Rs, and therefore we take area of this rectangle R to be R. This therefore is a very fantastic therefore, in the sense that the area, if you are assuming, is a continuous function of the sides. Nobody told us. It's a built-in assumption that, well, if the things are nice, things should be nice. They look nice, how could that be different? But there is no proof. There is no proof for that fact, that the area is a continuous function of the sides. We have to take an assumption that we want the area to be a continuous function of the sides, and therefore we can define the area of a rectangle as the product of the sides, even if the sides were irrational numbers. So this is a test assumption that the area of a rectangle is a continuous function of the sides. This is an assumption. In other words, we are already looking at the measure in a sense of continuous. See, you may see when we describe measure, when eventually, even when you are talking about probability measure, with some of you are very familiar, we have a certain where we put a very peculiar restriction there. I'll come to that question, but let me just make that comment here. We put, for example, if we have sequence of events, En, An, and if the ANs are disjoint, then the probability of the union is the sum of the probability. That's how probability theories do. If it's a sequence. Now this is because the fact that the old Euclidean dictum that the sum of the whole is equal to the sum of its parts. This is a famous way of writing by Euclid. So this entire thing must be equal to the sum of its parts, their distinct parts. However, will not be ever going to put infinite parts together to get a finite. So it would have been enough if you had assumed that if A1, A2, A100 are a finite number of disjoint sets, then P of the union is the sum of the P's connections, otherwise I am worried about the convergence, etc., etc. Why does one put this so-called countable additivity hypothesis in this thing? This is precisely to build in this sort of continuity hypothesis. This you could have removed that and said this looks more meaningful statement for me, that the area must be somehow a continuous function of that domain. So in other words, certain domains converge, the areas must converge. So you must talk about what is meant by domains converging, what is meant by events converging. Then the limit process. It turns out that's equivalent to this. That continuity hypothesis is equivalent to this and countable additivity. So that is why we put this. So therefore, this is not just a frivolous observation. It is an observation which has had a far-reaching consequences in the development of matter theory and probability theory. That the area is the continuous function of its size. Okay, so with that, we have that the area of any rectangle equal to product itself. Of course, subsequently what you do, if you know the rectangle, you know the right angle triangle. Once you know the right angle triangle, any polygonal can be divided, any triangle can be calculated. And once you know any triangle, any polygonal path can be divided into triangles. Triangulation, you can calculate the area of any figure bounded by a polygon. So beyond that, again, it is a curved boundary. You approximate as well as possible by polygonal boundaries and try to take the limit. And that's what argument is called in the method of exhaustion. Okay, go on exhausting all the tower area and then try to put polygons there and calculate the area. Right, so what Riemann did was the following. We start with this, then take any interval AB. We'll discuss these things later. But first, just I'll quickly go through Riemann. Take any closed interval AB, you may ask why closed interval, etc. But right now, let's take this. The reason for that was, again, in those days, it was all continuous functions. And continuous functions on a closed bounded interval, bounded, everything was nice. So they dealt with that only. Okay. So now, there are reasons for existence of certain things. Suppose I have a curve like that. So why it affects dependent things. Now we want to find the area. It is purely a geometric question. Okay. There's no calculus. Calculus will brought him to answer a geometric question. Right. So what Riemann did was, I will split this into small pieces and then calculate the area of each piece and then put them together. So this is what you call, I will partition this into. So okay, pi is a partition of that interval. Okay. Then take any typical interval, ij typical interval. Take that interval. Then for I will calculate this area. I will calculate this area. So area AJ is area under y equal to x in the interval that area around. And what Riemann said was, I don't know anything, I know only to calculate the area of rectangles. So what I will do is I will make two rectangles here. One rectangle overestimates this area, another rectangle underestimates this area. So how do I do it? At different points it reaches the different heights. take the maximum height it reaches. So let Mj be the maximum of Fx in x in I. See, this is all very funny that they are already writing maximum. How do I know that x is a maximum? So therefore, there is a tacit assumption that the continuity is there for them. Okay. So let's do it loosely. So what Riemann said was, for this is enough if I assume the function to be bounded. The moment it is bounded, it is at least having a supremum. So I can write there sup, take the largest possible. So in that sense, Riemann looked at bounded. So you can see that Riemann integral has several restrictions. It can be done, it is done on a closed bounded interval. It is done for bounded functions. Okay. For other places you have to readjust. This is the original one. Then look at the minimum. Then erect this. This is Mj and that is Mj. Erect these two rectangles. Calculate the area of those two rectangles. So we have Mj times, what is the area of the smaller rectangle? Let's call it as length of Ij. Okay? Is less than or equal to the area I wanted, Aj, less than or equal to Mj times length of Ij. Now what is this? This is of course obviously less than or equal to m times b minus a, where m is the maximum of f in the whole interval. Okay. Similarly, if I take only one interval, b minus a, as the no partition. The partition is the whole interval. First point is x naught, is a. Second point is then little m is the minimum of the whole, or 2 per n, whichever way you want. So therefore, I have this, and now I will add. I'm sorry, this is m times Lij. This is m times. If I add all these things, what do I get? M times the sum of all the small interval lengths, which is b minus a, less than or equal to summation Nj Lij j equal to 1 to n, less than or equal to summation Aj. If I add all those areas Aj, I get the area under the curve in that interval, yes, which is less than or equal to summation Mj j equal to 1 to n Lij equal to n. Right, but I have not done anything. I only got an overestimate of the required quantity and an underestimate of the required quantity. Now when I am estimating, if I am overestimating, I want the smallest possible overestimate. Suppose I get two overestimates, one is 10, another is 8. Since they are overestimates, 10 is a lousy job, 8 is a better job. So I want to take the smallest of the overestimates. So I want to take the infimum of all these fellows. Okay. Similarly, I want to take the biggest of the overestimates. So I want to take the supremum of all these fellows. Now, what do you mean by largest and supremum? This is some quantity which I will call it as, which depends on the function f and depends on the partition I chose. Similarly, this quantity depends on the function f and the partition I chose. So for any partition phi, m into b minus a is less than or equal to lf phi, less than or equal to a, less than or equal to b of phi, less than or equal to. So for each partition we get an upper estimate and each partition gives a lower estimate of the quantity that we want. So among all this, I want to pick the smallest one. Can I pick the smallest one? When these fellows are all bounded below, therefore they will have a infimum. These fellows are all bounded above, and therefore they will have a supremum. So therefore, m into b minus a is less than or equal to the supremum of LF pi over all partitions pi belonging to pi, the collection of all partitions, less than or equal to f, less than or equal to the infimum of uf pi, pi belonging to pi. And this is what is called the upper Riemann integral over the interval f, and this is what is called the lower Riemann integral of f over the interval. Right? The Riemann said, if these two are equal, then the AF is sandwiched in between the two, and that common value will be the area. So he said that f is integrable. I will call f, now we call it f Riemann integrable, if this upper integral is equal to lower integral, and in that case, that common value is called the integral, and that represents the area under the curve. So f is Riemann integrable. Integral upper f integral lower f. In that case, the common value is the integral. Okay, that's the basic idea of Riemann. Now let us, of course, when will this happen? For what functions will this happen? See, Prof, you said he gave a definition. Now, suppose the upper integral is not equal to lower integral for any function, then it's a vacuous integration theory. For no function, the upper integral is equal to the lower integral. Then what integral we have? None of my functions or interesting functions are integrable. Then it's a useless theory. So what Riemann showed first was, all continuous functions this will happen. If f is continuous in the interval I, then upper integral will definitely be equal to the lower integral. Then Riemann went a little further and said, if f has only a finite number of discontinuities also, at other points being continuous, and at these points where the discontinuity, you are playing it safe to start with, at these points where the discontinuity is, we'll talk about only jump type discontinuities. So then also it is okay. But then later, it's that even infinite number of discontinuities are there, I don't care. As long as I have a bounded function, and if it has an infinite number of discontinuities, but as long as final verdict on it is, with the set of discontinuities, you are back to a set of discontinuities. See, these are the fellows you have to be controlled. If the set of discontinuities is of Lebesgue measure 0, then the function will be Riemann integral. We will see that later. Okay. So final thing is, f is a bounded function f on an interval ab is Riemann integrable if and only if this set of discontinuities is of measure 0. So that was completely settled. We know exactly what sort of functions. So in other words, you can actually fool around with the values and a large set of points. As long as they are set of measure 0, it's fine. Still, you can have everything same. Nothing is destroyed. Okay? So that is where I said that equivalence business comes into the picture. Function doesn't mean a correspondence. You can fool around with the correspondence at a fairly good collection of points. As long as they are set of measure 0, nothing is destroyed as long as integration is concerned. Okay, that's all that we have to see later. So therefore, Riemann had this is called Riemann integral. So now let's look at what actually Riemann did. And when we look at this and look at its generalization, we get what is known as the level integral. Okay? And that's what we'll start next time. From here, we'll pick up. So this is exactly Riemann. Now, Riemann had one fundamental defect. Namely, you can have a sequence of functions, each one of which has a Riemann integral, and the sequence converges to a function f pointwise, but then the limit function is not Riemann integral. That is the devil function of Dirichlet. You can get a sequence of functions which are continuous except at a finite number of points and therefore Riemann integrable. But they convert to this devil function of Dirichlet, which is not Riemann integrable, because it is discontinuous at every point. Its upper integral is 1 and lower integral is 0. Fx equal to 0 at rationals and 1 at irrationals. Upper integral is always 1, the lower integral will be always 0, so they never match. The devil function is not Riemann integrable, but every member of the sequence is Riemann integrable. So from the limiting point of view, even to ask this question, if Fn converges, yes, does it imply Fn Riemann integral? Even to ask this question, it is not meaningful because we don't even know whether the integral f makes sense. Okay. So therefore, from the limiting processes, Riemann integral had a major defect. And so some of these things we have to handle. And that's where Lebesgue comes in. He looks at this whole thing in a different, he looks at Riemann. He said, what did Riemann do? I will do the same thing but in a different way. So there is a famous quote. What is this? What is that say? A genius doesn't do different things, but he does the same things differently. And that's what Lebesgue did. He didn't do what? He didn't do anything different from Riemann. He did the same thing in a different manner and he got the access. So that's what the big thing about Lebesgue, and that was his thesis exactly about 100 years back, 1901 or something like that. Lebesgue's theory. Then that's what I will start from the next class. Again, I'll write the